Manufacturing Insights, Manufacturing Engineering Magazine's video series for process improvement. This program explores high-speed machining technology and how it's being employed to quickly and economically machine quality products. We'll focus on 4 companies and what they've done to successfully implement and apply high-speed machining systems. Our first stop will be at Trutron Corporation. At first, management was skeptical that high-speed machining could deliver on all the performance claims made. But once experiencing its benefits, Trutron management has embraced high-speed machining as a strategic direction for their company. Next, we'll visit Protomatic Incorporated, a high-quality prototype and short-run production machining company. Protomatic began investing in high-speed machining to offer more competitive pricing. But first, they had to overcome some coolant and tool vibration problems. For this, Protomatic relied on outside vendors to identify the problems and fine-tune their cutting process. Next, we will see how Gossiger 3D, an applications engineering company, is working with its customers to replace time and cost-intensive processes such as jig grinding, wire EDM, and hand finishing entirely with hard milling and high-speed machining. Gossiger 3D says it can improve the quality of finished products while significantly cutting production time. And finally, when Metal Fab Incorporated was looking to improve production, the job shop had a unique need. The company makes a lot of prototypes, many with tight corners and small, intricate pockets. To quickly and cost-effectively produce these prototypes, Metal Fab looked at every aspect of their high-speed machining systems to maximize production. The term high-speed machining, or HSM, has been in the lexicon of manufacturing terms for a long period of time, but the process has only gained in acceptance in recent years. This increasing recognition is due to high-speed machining's synthesis of technological advances that, when combined, allow manufacturers to reduce cycle times, increase throughput, shorten machining time, and minimize non-machining time while yielding high-precision parts having a favorable cost-performance ratio. Typically, high-speed machining is accomplished using spindle speeds that range between 12,000 to 30,000 RPM and higher. These spindle speeds are coupled with rapid axis movements, transverse rates, accelerations, and decelerations to maximize material removal. Generally, high-speed machining is performed using a shallow axial depth of cut in order to achieve good surface finish while avoiding damage to the workpiece, cutting tool, or spindle. But high-speed machining is much more than simply running a cutting tool at maximum feed rates and taking multiple shallow cuts. In fact, this approach to machining can be less efficient than taking fewer passes having somewhat greater depths. The ultimate goal of high-speed machining is to produce a finished part in the least amount of time. This is accomplished by reducing inefficiencies in the cutting process, by maximizing the relationship between speeds, feeds, and depth of cuts, and by completely integrating the various technologies that encompass the high-speed machining center, its tooling, and the programming and software. There are a variety of advanced high-speed machining centers available. The best are characterized by a compact, rigid, and robust design. They should be powerful, provide extremely high spindle speeds and acceleration, be equipped for near or completely dry machining, offer options such as additional tool storage and tool monitoring, supplementary part fixturing, and fast part delivery and removal. The machine control system should be fast, responsive, and flexible. It should have interpolation capabilities, subprograms for complex part machining, and the ability to totally integrate with other in-house systems. Direct connection of the motor to the spindle is preferred over the use of belts and gear drivetrains. Because these integral spindles are coupled directly to the motors, they can accelerate and decelerate faster than the drivetrain systems. High-speed tooling must be able to withstand the increased spindle speeds, feed rates, and heat buildup in the process. Hollow shank taper or HSK tool holders were developed for high-speed operations and are preferred over conventional CAT V-flange or steep shank tool holders in many applications. Hollow shank taper tool holders offer the advantages of high torque transmission, high repeatability accuracy, excellent adaptation to high-speed cutting, uniformity, minimal runout, high clamping force, reliability and safety, and static and dynamic stiffness. How cutting tools are clamped into the tool holders is also very important. The three primary cutting tool clamping systems used for high-speed machining are mechanical, hydraulic, and thermal. The success of any cutting operation is determined by what happens at the point of contact between workpiece and cutting tool. There are a variety of cutting tool materials, both coated and uncoated, and cutting tool geometries used that offer better than average toughness and good heat resistance for high-speed operations. An initial pitfall companies face when first using high-speed machining is attempting to reuse conventional programming and software. Using software intended specifically for high-speed machining operations will yield superior quality and consistent optimized results. Also, extensive training is essential for all employees involved so that they become comfortable working within the parameters of high-speed machining. The Trutron Corporation in Troy, Michigan began using high-speed machining in the late 90s. What initially piqued Trutron's interest in high-speed machining was the time savings the new machinery could potentially bring them.
What we were looking for in the high-speed machining arena was twofold really for our company. We do a lot of sinker EDM work here. So the creation of graphite electrodes and copper electrodes takes a tremendous amount of time. We were looking for a piece of equipment that could aid in that and eliminate a job position per se, utilizing that person somewhere else in the company, but not consuming so much of their time. So one side of it was the creation of electrodes. The other side was strictly machining hardened steels or non-graphite products that would allow us to streamline our processes and increase our throughput by maintaining consistencies in our part quality.
In addition to offering electrical discharge machining services, Trutron Corporation expanded its operations to produce constant velocity joint tooling and fluid-powered pump parts. This type of machining required great precision to produce a final product.
There's a skill set that people have in this business, and it's very important when you have a niched business that you maintain those skill sets. It's difficult to train people in very precise, close tolerance work, and the type of high-speed machining that we were looking for was very high-quality, precision machinery. The high-speed machines work on heat-treated materials up to 64 Rockwell. We cut very thin features, deep features. It allowed us, moving into this arena, allowed us to eliminate OD grinding operations, jig grinding operations, things that we would normally have 8, 10, 12 additional sequences in are now done in 1 or 2 operations on the high-speed machining side. So it's really been able to streamline our process.
Part of streamlining Trutron's high-speed machining process required changing to software designed specifically for high-speed machining. Trutron selected Esprit software to create high-speed tool paths because it was flexible enough to meet all of their needs. Engineering manager Mark Coors explains their process.
The programming process consists of creating a solid model if I don't receive one from the customer. If I don't, I usually receive a 2D print and I have to recreate the solid model inside of SolidWorks. From there, I'll read the solid model into Esprit and create the cutter path. there are multiple operations inside of a cutter path depending on the complexity of the part, multiple tooling, multiple settings as far as feeds and speeds and step overs. After the cutter path is created, depending on which machine I'll be sending it out to, that will be the particular post that I'll use. So at that point I'll post out the NC file and send it out to our machine.
When I get the part program sent out to the machine from Mark, what I would first do is run a graphics on it. I would edit the program beginning and end so that the lead out and lead in is correct. Edit any M codes for coolant, tool changes, oil air mist. If the part was run on an angle and we had transferred the coordinate system, I would put that into the program, letting the machine know what position the part is in before it actually runs, and it would skew the coordinate system accordingly.
Trutron Corporation uses HSK tool holders in their high-speed machining operations. Joe Adamski explains its benefits.
What we use here is an HSK holder. What you're looking at is a 40E. This is meant for high-speed machining. It is balanced to 42,000 RPM. And the nice thing about this is it's got a very short taper. It is a hollow end shank. And when you put this into the machine, the grippers will actually come in, grab the tool holder by the inside, pull it back up into the spindle, creating a very, very rigid tool holder. It's supposed to be 2 times more rigid than a cat-style holder. And with that, you can increase your depth of cut, your RPMs, your speed and feeds, all without sacrificing any rigidity or part tolerance.
Over time, Trutron has found that the key element to making a successful transition to high-speed machining is being open to change in all areas.
You have to pretty much throw out the rule book of conventional milling. You have to take a look at your tool holders, your end mills, the part that you're machining. How rigid is your setup? What style NC code are you using? Are you using conventional style milling, climb milling? Are you constantly on the part? There's so many different things to look at. Don't be afraid to experiment. Don't get frustrated. Don't be afraid to try. The guidelines that you get from cutting tool manufacturers is only a place to start. They're not using the same tool holder as you, the same machine, NC code, material. It's a good place to start, but you can always improve and just keep trying.
Protomatic Incorporated, based in Dexter, Michigan, is a high-quality prototype and short-run production machining operation. Protomatic was interested in high-speed machining for price point and performance, as Doug Wetzel, Vice President and General Manager, points out.
In a more competitive market, you need to be a little more aggressive on your pricing, so therefore we were enticed into looking for new avenues to improve our efficiency.
In business for over 30 years, Protomatic offers in-house design services and prototype manufacturing to clients in the automotive, electronic, medical, and optical fields. While Protomatic has officially been using high-speed machining for the past 3 years, the transition to it was a natural evolution.
I think we've been high-speed machining much earlier than that. We just didn't know it. And we always pushed our technology to the limit. When you have a 10,000 or a 12,000 RPM machine, you're going to, of course, push it to the max. And the carbide can take it, the machines can take it, and of course the parts are manufactured quicker.
The conversion from conventional machining to high-speed machining has helped Protomatic to maintain and then subsequently gain market share in several areas of business.
The most prevalent is applications where people need low weight, high strength applications where castings cannot create the strength that a billet would. And the other application is simply trying to penetrate into the casting world. We have many applications where they would have typically been done with lost wax. or permanent die type of casting, and we simply machine them from billet. And it's more cost effective to do that in low quantities.
The use of high-speed machining also magnified common machining problems, such as excessive chatter and vibration and coolant issues. To address these problems, Protomatic sought the help of D3 vibrations and machining efficiencies. Both companies are consultants who specialize in achieving optimum performance from high-speed machines.
When I first approach a problem, I listen to it acoustically. I want to see what is going on in their process. And when we listen to it acoustically and we get the parameters that they're running, their RPMs, number of teeth, things like that, we can, I can look at it and see, well, is there chatter present or is there not? Most people can tell if there's chatter or not. That's not the great idea of the technology. But if it is chattering, we know what frequencies are chattering and we can go after those. Many times we can fix a problem just using our acoustic method if it is chattering. Our technology tells you exactly what RPM to try to find that sweet spot. If that fails or we want to go the next step, we use the hammer and accelerometer technique called modal analysis. And which modal analysis is nothing special to myself and my colleagues. They use it in many industries. But we use it much differently than what other vibration companies might do. And we get that fingerprint of the tool stack up so we know what that tool is in the given system. And we take the tests and then we make a stability diagram.
The stability diagram not only provides information regarding the ideal speeds and depth of cuts for chatter-free machining, but also a window into the regions of the machining process that are problematic.
There's this region, which I call the poor man region, which is the area we really don't want to run into. The red area is chattering, and you can see there's no real good white spots to run, which is where it's stable. So almost anywhere running those depths of cuts and those spindle speeds, you're going to have a chatter problem and consistently won't be able to run there. We try to get people into really what we call the high performance region. And the high performance region is right above the high speed region. And we can see that there are areas that you can get high depths of cuts when you choose the correct spindle speed. This is kind of like adding stiffness into your system. By choosing the right RPM, you can oftentimes make your tool act like it's 3 or 4 times stiffer than what it really is.
Once D3 vibrations identified the optimum speed, depth of cut, and feed regions for Protomatic's high-speed machining operations, machining efficiencies came in to examine their entire machining process.
The first thing I do is look at the end result of the cutting tool and the workpiece. We then take a look at the stability of the structure of the fixture, the flooding techniques, the quality of the coolant, cleanliness of the coolant, and pretty much a checklist of 9 various elements that go into making a good part.
This checklist of 9 elements includes the part and process design, the part material and hardness, the blank manufacturing quality, the tool